right, so today's lab's pretty basic. I think you guys will probably finish a little early, so that's good because it's a nice day. So we're going to do the theme of sort of this whole section is waves and optics. And so everything we're going to do is going to be about either waves or optics, and the waves and optics are pretty much connected. So we're going to start with standing waves on a string. So we're going to vibrate a string, and we're going to see standing waves. So I'm going to talk about traveling waves and standing waves so you get an idea of the difference. So here I have traveling waves. So I have a graph here of the amplitude, which I call y, or a is the magnitude of the amplitude. And then I'm going to plot it versus time. And so if you want to write this as a function, you can write y as a function of time is equal to a, the amplitude. And I picked cosine omega t. I could have picked sine, right? Both are waves, but I wanted to start up at the top here, which is my personal preference. And so the question is, what is omega? This is a Greek letter omega. It's a frequency of sorts. It's called the angular frequency. It happens to be equal to 2 pi f, and since f is the frequency and it's 1 over the period, we can write it as 2 pi over the period, which is capital T. And the period is the time it takes to repeat itself. So from peak to peak is a way to repeat itself. So from here to here is a period. Also from here to here is also a period. From here to here is a period. And you can infer other periods from there. But the period is always a length of time, and it's the time it takes to repeat itself. Any questions on this? All right, let's do standing waves. So standing waves are similar, except they stand instead of move. So I have the same thing over here. A is the amplitude, and it's going to move up and down as a function of x now. So if I write y as a function of x, it's equal to a, the amplitude, cosine kx. All right, so over here it was omega t, and over here it's kx, where k is 2 pi over lambda. Lambda is the wavelength. It's the time, it's the distance it takes to repeat itself. So from peak to peak, or from here to here, or from here to here. And k is called the wave number. All right. And the reason why we use omega, the angular frequency, and k, the wave number, instead of the time period or the length to repeat itself, the wavelength, is because we're lazy. Physicists get tired of writing 2 pi f over and over again, and so we make up a new symbol, and we call it omega, and we get tired of writing 2 pi over lambda over and over again, so we make up a new symbol, k, and we call it the wave number. All right, so I just want to remind you guys the units. Amplitude will be in meters, SI units. Omega will be in inverse seconds, right, because it's 2 pi over a time period. Frequency is in hertz, which is also inverse seconds, but we give it a different unit to distinguish it from angular frequency because they're off by 2 pi. The wave number has inverse meters, and the wavelength is in meters. Any questions? All right, so can I borrow somebody real quick? Anybody? Just stand up. I'm going to demonstrate a little bit with this slinky thing what we're talking about, just in case you guys didn't know. You can just hold it like that. So I'm going to try to do a standing or a traveling wave first. So that one's the easy one. You see it moving, it went over there, and then it gets to him and it bounces back, right? Hold it tighter. All right, there you can see it. All right, now the standing waves are a little harder because you got to hit resonance. All right, there's one right there. If I go faster, I can get the second one. Just hold it stiff. There you go. So there's the second resonance. And if I'm having a good day, I can get the third one. Not going to happen today. All right, so we're going to do this. We're going to set up a weight over here that's going to add tension to the string, and then we're going to use a mechanical vibrator to vibrate it. And you're going to see what I just demonstrated, except you won't have to get your arm all tired because, you have a mechanical vibrator doing the work for you.
Are those Ks on other sides of the lines?
No, this is just pointing out the length here,
Oh.
and then this is the wavelength. So what you see there is you're going to see a pattern like this, but this is going to be going so fast that it kind of just looks like a mesh of blob here. And I want to point out that this is the wavelength. So it's 1, 2, 3 minimums, which we call nodes, where the string doesn't move. Or if you count from here, 1, 2, right? I mean, you could do from peak to peak, but this is not. This is half a wavelength, because actually when the string's up here, the other part of the string is down here. Does that make sense? And so actually from peak to peak would be somewhere imaginarily over here, which is the wavelength here. All right, the velocity of a traveling wave, we have a formula for that. The velocity is equal to the square root of the tension over the mass per unit length. And so F sub t is the tension, has units of newtons, force, and then mu is mass per unit length. It's called the linear mass density, and it's kilograms per meter. And so usually what happens is the velocity, and so you can adjust how much tension is in the string. So if I, or you could pick a different string. So let's say if I double the weight of the string, which is double the mass per unit length, what happens to the velocity? Holding the tension constant, same tension. Gets smaller, right? All right, so maybe I should say if you go 4 times as much mass, the velocity would go half as fast. Okay, and if you use the same string, but you double or 4 times the tension, then you'll get twice the velocity, right? Now sometimes in some mediums the velocity is held constant, so these guys will you have to know what's constant in the system. All right, but the definition of velocity is the change in x over the change in time. But in this system, the change in x is the wavelength, and the change in time is just the period. And so if I change the period to a frequency, I get that it's equal to lambda f. So this is another formula that shows up a lot. The velocity is equal to lambda times the frequency. All right, and so if velocity is held constant and I double the frequency, what happens to the wavelength? If this is constant and this guy increases, what does this guy do? Has to decrease, right? And so they're inversely proportional, the wavelength and the frequency. So if I double the wavelength, then the frequency would have to drop by half. And if velocity can change, then you can analyze this equation however you like. So the steps we're going to take to do this is we're going to pick the tension in the setup, which happens to be equal to mg because we're hanging a mass. That's what's setting the tension in the string. Then we're going to find an f, a resonance frequency for a standing wave. And how are we going to find that? Well, it's on the box. You're going to adjust the frequency of this guy by adjusting the frequency on the box. You're going to measure the wavelength with a meter stick. And then you're going to multiply these two together to get the velocity of the wave. Now the velocity of the wave, it's a standing wave, so it's not really moving anymore because it's at resonance, right? But if you stop shaking it, the wave would go, hit the other end, and bounce back. And so it's in resonance, so like when the wave comes back, it's constructively interfering, right? So there's sort of a velocity there that you can't really see. And then we're going to plot the velocity squared versus the tension. Now if we do that, we can analyze this equation to determine what the mu of the string was, the mass per unit length. Any questions? All right. We're also going to directly measure the mass of the string. We're going to get 10 meters of string. We're going to measure it, divide it by 10, and we'll do a percent error. And they usually are pretty close, 10, 20%. All right.